Thank you very much. Thank you for inviting me again and again and again and again. It's very nice. I'm also surprised there are so many from outside Brazil. Maybe they are running from the summer. Came to pick up some winter. So I didn't sign my name on purpose because the three other authors are more important. They were all my PhD students. Two of them. I cannot manage this. Can you see here? Wait. Okay.
It's invisible to someone with red-green color blindness.
Okay. Anyway, two are women, so I'm doing my job. You know, there is this important meeting in IMPA. I'm trying to announce it a little bit. It's an event about women mathematicians. This is 2 days on 27, 28. Unfortunately, most of you will be here. And of course, at this one, you would rather know the first name, Maral. Huh?
Point with your finger. I cannot see that.
You cannot see this?
No, I've seen absolutely nothing.
Oh, gosh.
No, nothing at all.
Here, Maral. Her name is Maral. She should be here somewhere. Maral? Okay. Anyway, so this is an almost finished joint work, but most of the things that I'm going to tell here are proved. There is one slightly doubtful theorem. Okay, who is the main character? Hankel is supersymmetric. So this is a square matrix, which is symmetric, but supersymmetric. You know, along the entire diagonals is the same. But it's also important to have the non-necessarily square model. And it goes the same way. I'm going to keep this notation where the number of rows is always at most the number of columns. And it's interesting to know that for these matrices, you are using the number of variables is the summation of the number of columns and rows. I mean, it's a very classical object, so one needs to do some commercial about these Hankel matrices because many people never heard about them or never cared. So these are some samples, some commercial. Let you read if you like. Some people like to read what they wrote in the slides. I think this is very disturbing. So just let you read. Okay.
Why was that more than symmetric? This looked like a symmetric matrix.
You did, but I go back.
Okay.
Supersymmetric.
Yeah, what does that mean?
Along the entire diagonal is the same guy, completely. Not just symmetric, along the entire diagonal. Now let me put my finger again. X3, 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 X4 goes on, XM, XM. Okay? Super. Okay. Maybe Teplitz matrices are more famous, at least in analysis, optimization, because they use it more. But it's the same. Instead of going anti-diagonal, you go diagonally. It's same properties, same ideas. So here's some more. I fetched this, randomly from some books, sufficiently recent books. And again, some more commercial. So it's used quite a bit in analysis, in various areas of analysis. And this is again fetched from some book, which is fairly recent. Okay, so this is a subject that has infinitely many papers in these areas. I'm not kidding, infinitely many, if you care to look at. Now, but we are finitely many in commutative algebra. So let me give some sources. So the first one is this, the first one I know of course, existed before because was defined by Hankel, not with this name. Hermann Hankel was the German mathematician. So this is interesting in famous book on invariant theory by Grace and Young. Then there is this famous book, this English author, Room. This is a very much quoted book, this book by Room, but you know, just few people really read it throughout because the language is sort of hard. Daisy Eisenbach, this is an incredible landmark paper. Then there is, I think the first time that someone really collected the algebraic part of this Hankel matrix and idea was Watanabe. This is Junzo Watanabe, not Keiichi. Aldo Conca from Genova. Very important paper on Hankel matrices. This is a paper which is not about Hankel matrices, about homoloidal polynomials or hypersurface, but at the end there is a study of Hankel matrices with respect to homoloidalness. This is a paper with one of my collaborators. Again, this is called catalecticon, but sometimes these words are interchanged, catalecticon and Hankel, but this is not so good because catalecticon is something slightly different and has different meanings depending on what are you doing. So once I used this word catalecticon, Tony Jeramita said, but this is not catalecticon. I say, it is, but it's not. So there is this several. Here's Maral again. And this is a paper with Maral and several collaborators where they show something important, that determinant Hankel are rational singularities. Okay, so let's start a little bit. First, the generic. So this is my notation for the ideal generated by T minors in an m by n matrix, any commutative ring. This is the notation that I have at the beginning for a Hankel matrix, which is not necessarily square. So here's the classical properties of Hankel minors. Call this resilience. This is a typical and very fundamental property of Hankel minors, which tells you more or less that you can reshape the shape of the Hankel matrix and go up to the case where the minors are maximal minors. So this is not clear who was really the first to observe this. As commutative algebraists or algebraic geometry, more or less, this is attributed to Gruison and Peskin in one of their famous papers on classification of curves, space curves. But people tend to quote this from other sources as well. So the codimension, which is algebraist, this is same as height in this context. So it always has this codimension. In some sense, it is an extreme codimension if you are in a larger space of matrices, like taking generic and symmetric and so on. And the nature. So this ring is Cohen-Macaulay and normal, besides being the domain. So these ideals are always prime ideals. So this is what is known classically For instance, you can find some of this in the paper by Eisenbach that I quoted before, and also in the paper by Watanabe, and certainly in the paper by Konka. Okay. So this talk is really about some degenerations of the Hankel matrices, mainly in the case of square matrix. But of course, we have to use some non-square matrix as well in the same shape of degeneration. So let me explain what kind of degenerations we have in mind. So the degeneration we have in mind is the ones that are result of from applying a ring homomorphism to the entries, to the original entries on the base ring. So let me state perhaps two basic features. First is, so it's induced by a ring homomorphism. And second, since I'm starting from a matrix with variables as entries, then I can just define a homomorphism by mapping the variables. So one chooses to map the variables either to itself, a variable either to itself or to zero. This is the only possibility. This kind of degeneration were studied by other people, but not with the same focus. By other people some, I don't know, 20, 25 years ago, but with a different focus. And of course, some of this you find also in the paper by Eisenbach, also with a slightly different focus. Okay, this just assures that if you are on a certain category, in a certain class of matrices, you don't want to get out of this class, then this is the right way to do. Because if you start with symmetric matrices, then the degeneration will be symmetric forever. If you start with the Hankel, it will be Hankel forever. No? But instead, if you don't require this, you can start with a generic one and just put a zero somewhere that has no meaning whatsoever. It doesn't come from homomorphism. So it could be symmetric and stops being symmetric. So it's a way to keep inside the class of matrices that you are studying. Now, tidy, let's see. By tidy, I mean that I'm going to organize more or less the degeneration in an apparently special case, putting zeros like this, or like this, or like this. So always on the left, on the right lower corner. And you can ask, why this shape? I say, because this is the only way, the only one I can work on. It's also possible to put zeros throughout here in the same way, and you still get some lemmas and propositions, but it's not clear whether you get the same results exactly. And if you put the zeros just randomly, then I don't know what happens. I have no idea. So let's look at the minors as we did for the generic case, now at the degenerated case. So we need some notation. So this H sub m R in brackets is this Hankel from the previous page. Let me go back a little bit. So it's any of this, where R means the number of zeros on the right column here, and of course, if you remember that this, perhaps if you remember that it came from the generic case, then we are making as many x's go to 0 as R, because this was a Hankel matrix. If it is a symmetric matrix, you have to recalculate a little bit. But this is very easy. So it keeps like this. Just reminding you that R equals 0 is the generic matrix that we talked about at the beginning. And this, the other extreme cases was dubbed sub-Hankel matrix because it has very special properties. So here is a proposition about these minors. So suppose again that you have, I'm always going to keep more or less this range. you know, can go to 0, from 0 to n minus 2. The reason, maybe I should explain this in a minute, go back a little bit. You see, if you increase by 1 the number of zeros, then you have a trivial matrix. You don't want to consider it. Okay, so first thing is the codimension. So for any ideal of minors or T minors, you have this as a minimum of these two. So this one is the one in the generic case, and this is one that accounts for the R. So it's a minimum of the two. It's still called Macaulay. This is special for people in singularity theory. They are using quite a bit Cohen Macaulay, you know. Finally. And this is a prime ideal only in those cases when T is 1 or at least R plus 2. So it depends on the R, essentially, or T, if R is fixed. In particular, if you take the ideal of submaximal minus, which is very important in this talk, it has codimension 3, and it's prime if and only if R is less or equal than n minus 3, which is okay. We're just missing the extreme case, the sub-Hankel, but otherwise it's a prime ideal. You're going to ask when it's normal. Forget it. Difficult. Maybe very seldom. Okay. Some commercial for submaximal minors before any theorems appear. So first of all, you're just one single stretch away from maximal minors by this Grison-Peskin, you know, stretch. You just stretch it one time, and then you get maximal minors. And of course, we expect that maximal minors are easier, in some sense. They are cofactors, okay. And in the square case, they are intimately related to partial derivatives. How? Okay, so I'm just saying. The first one depends on being Hankel, I already explained. It's completely false for any other kind of matrices, unless, I don't know, unless it is tuplets. While the second is good for any matrix. The last one is an interesting result, which you may not think about it. Goes like this. If you take any square matrix, such that the entries are either variables or zeros, then the partial derivative with respect to any variable, you sum up the cofactors with sign of this variable in all slots that it appears as an entry. Can I write an example? Is it possible to see? No? Here's the famous skew symmetric everybody has taught this, something like this. So the syzygies of the variables, 3 variables. Okay. So you see the determinant is 0, and if you care to compute the summation of the cofactors with signs, you get zeros. It's not so obvious. Just because the determinant is 0, you can get all the sums to be 0. And of course, they have to be, otherwise this guy is false. Anyway, so just a reminder of how you can prove this. Proof is not difficult, but you know. Anyway, so let's go on. Now, what is this fiber cone? Has several different names, adjectives. Fiber cone algebra, fiber algebra, special cone, blah, blah, blah. Okay, this is like the idea of Hilbert. You know, sometimes you look at the ideal, sometimes you look at the subalgebra, sometimes you look at them together somehow. So here's a definition. So you can take any matrix over standard graded polynomial ring. You can even trade the K for a Noetherian domain, if you like. And you assume that you have a matrix such that the matrix is homogeneous in the sense that all 2 by 2 minors are homogeneous. For example, when all entries are homogeneous of the same degree. Then you can consider this algebra. This for me means the linear system of the ideal generating degree T. So you can take the ideal or you can take the subalgebra. So if you take the subalgebra, then this is what's called the fiber cone of phi. Or should be called the T fiber cone. So anyway. So here is a result that's very useful, and the proof is very simple. I call it Bruns Vetter or possibly folklore. I don't know. It's proven in the book by Bruns and Vetter. The proof there is in generic case, but you can see that it applies in other cases as well. If you have any m by n matrix whose entries are either variables or zeros, this is what I'm interested in, but it can be more general, such that you have a non-zero maximal determinant. So we are going to apply this especially in the case where the matrix is square. So I'm saying that the determinant of matrix is non-zero. Then if you look at the submaximal minors and take this algebra, this fiber cone, it always has maximum dimension of the ring itself. This is the half of the dream of any guy that looks at the rational maps. This may be birational. Has the right dimension. So one of the consequences is the following, because we had this resilience property. If you take an ideal maximum of any coordinate-wise degeneration, remember coordinate-wise was obeying that law, those features at the beginning, then the fiber cone has maximal dimension always. And I'm just giving an example how false this is for matrices in general. The simplest example you can think of. You take even a Hilbert merge matrix or 3 by 4, and you see that the 3 minors have a relation. You can easily compute this by hand. So it's not 3, of degree 2 is 3, what you expect to be 4. But just as a slight check, if you look at the 2 minors, which are the submaximal, then they have the right dimension, the cone, which is 4. Okay, so immediately there are some open questions that we cannot solve for the moment. Maybe some of you are interested in looking at them. So first of all, we expect this ideal, the fiber cone of this ideal to be a Cohen-Macaulay ring for any T, for any R in the range. The homogeneous defined ideal, the fiber cone, should be, we expect, generated only by quadrics and cubics. This is a typical situation in many other cases which have nothing to do with Hankel matrices, but I think this is the case as well. Of course, the usual thing, you computed many cases for small values, then the computer say, then you stop and say, maybe it's a conjecture. But since nowadays you make a conjecture, then the other guy immediately goes to a more powerful computer and has a counterexample, you just ask questions. So there is algebra, which is this more sophisticated object, but many people know it as a blow-up. It's Cohen-Macaulay in fiber type. I think fiber type was mentioned by Susan, but in a very brisk way, no? She meant maybe also the fiber type. No. Nobody paid attention. So fiber type means it's a very technical thing about the Rees algebra. It has to do with the shape of the generators of the defining ideal of the Rees algebra. So I don't want to explain this well, but it's something very interesting. And again, you know, there is some evidence, computation, and also theoretical a little bit. And we don't even know it's going Macaulay. So these are two different questions. Eh? This is the nature of it, and this is the shape of the defining. I'm just saying what is the result for those that haven't seen the definition. It can also be identified with the usual direct sum of the powers of the ideal. Now, I say explain the fiber type when I have 1 hour talk. This is impossible. Okay, now comes something new. So throughout the rest of the talk, we assume the coefficient in the ring has characteristic 0. Many things still work out, but not really in general. So let me call J the ideal generated by the partial derivative of f. Remember, we are back in this case notation. This is a square Hankel square matrix with R zeros on that column. And now you take the Jacobian ideal or gradient ideal of the determinant. This is a venerable guy. And now you compute the codimension, which is something that should look obvious, but the proof is not obvious at all. You expect it to be 3, except in this extreme case, you expect to be 3 because it is 3 for the symmetric matrix. And then you expect, well, I mean, we degenerated a little bit the symmetric matrix, but it's still okay. So it is expected and not totally obvious. But this, anyway, this is the preliminaries. Okay. I'm just explaining here how I have to use a little bit the cofactor formulas, the Cauchy formulas, and blah, blah, blah. Ah, yeah. I wrote this to remind myself to say this, that the reason why it does not specialize so well from the symmetric case is this problem, because derivatives do not specialize. Minors do, but derivatives don't. So if you have sufficiently many derivatives or sufficiently many minors which are derivatives, then you are close to doing some specialization, but you still have to care about this. In the prime ideals. So we still don't know about the embedded prime ideals. We have again some question or maybe conjecture. But the others, we know a little bit more. So if R equals 0, this is generic case, then the submaximal minor is the unique minimal prime of J. Remember, J was this gradient ideal. And remember that the partial derivatives of J are cofactors, but there are many cofactors which are not partial derivatives. So the conjecture is that if you go one step further, it's the only embedded prime. And again, you know, you verify in so many cases, blah, 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 but no philosophical reason behind. Well, there is some reason behind. If you look at the generic case, you know, these minors tend to be the singular locus, blah, 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 some stratification. Now, the sub-Hankel case, this, you see, it's completely degenerated because the minimal prime look like this. You know, they are not really ideals of minors anymore. But you see, what looks very bad, in fact, is very good for other purpose. So in the other cases, we have this. The minimal primes of J are the submaximal, always somehow, and the ideal Q generated by the m minus r non-zero variables of the last column. So I don't want to go back all the way, but you remember there were zeros here, then there are variables which are non-zero, and then you take the ideal generated by this. So you see in general they have different codimensions. So these ideals this J tend to be very bad. It's not even unmixed in general. And certainly not clear that's reduced either. And the conjectures, the embedded prime ideals are, the next one, and also this strange one where you take again this non-zero and then add up this. Okay, at this point becomes a little bit technical. Now, what is my time? Still there. So this is again some folklore. If you take any subalgebra whatsoever, finitely generated of the polynomial ring, then its dimension is the rank of the Jacobian matrix. This is really, really, really characteristic 0. There's a story about this. I don't want to spend any time on this. Okay. So in the case where the generators of your algebra are the partial derivatives of some f, then this is called the Hessian matrix of f. It's denoted like this. Its determinant is called the Hessian of f. And let me call f of j the fiber cone that I defined early. Only this case for j. So this is called the polar fiber cone. And the dimension, because of this general proposition, is the rank of the Hessian. Okay, now this is a proposition which is technically hard to show. We have a very long proof and many, many ideas how to make it shorter, but always at some point you have some obstruction. So you still have this very long proof. Don't want to talk about it. It's very technical. And the polar map is this rational map defined by the partial derivatives. And remember that this is dominant. So the image is the whole of the projective space on the right side. So you have a polar degree, which is the field extension degree. You take the field of fractions of the subalgebra generated by the partial derivatives, and the one generated, or the one of R generating degree of m minus 1. So this is the degree. And it raises the natural question, when this degree is 1, or said otherwise, when the polar map is birational. In this case, you have a Cremona transformation. Or you also say that f is homaloidal. Okay, I'll discuss this in a minute. So let me say very quickly about the dual variety. So let me go on a little bit. So the dual variety is it's like the polar image, only that you restrict to V of f. Or if you want algebraically, you go mod the ideal generated by f, then you get this dual variety, also called the Gauss image, because this generalizes to Gauss image. But in this case, just the dual variety itself. This is the notation. Now there is this famous equality by Sager, where the dimension of the dual variety is the rank of the Hessian modulo f. So you have to compute it modulo f and then subtract 2. So you can apply in one case where this coordinate-wise degeneration that I am considering is also m plus 2 ladder-wise. This is technical, but it's easier to look at the definitions. So first, you divide two blocks where the sum is at most m plus 2, or when the sum is larger than m plus 2, and you require that everything that is in the first block should not, and the second block should not map to anything before. You know, this is ladder-wise, so you assume that you go step by step like this. No better name for this. We found this one. Now, in this case, there is an impact, and you can show that the dimension of the dual variety is at least n-1. Okay, another question which is very much tied to this is when is the variety of f itself a component of the Hessian variety? Or if you want algebraically, when is f a factor of the Hessian? And then what is the multiplicity of this factor? So this is a classical thing that was studied by Segre. And the impact is that if you know quite a bit about this, then you notice that the dual variety may fail to be a hypersurface. So it's defective in the language of, not defective in the language of Coulomb. So here's the result of Segre, it's a little bit technical. So if it is a factor, then the multiplicity, the expected one is, well, I mean, the theorem is at least that, the expected one is this, exactly. Now, again, some conjectures. Well, at least we have a proposition which is not a conjecture. This is for this extreme case where the guy is self-dual. It's the only case where it's self-dual, otherwise. So here's conjecture. F is a factor of the Hessian determinant with the expected multiplicity, the one defined by Segre. The dimension is m-1. And there are some more, gets more and more detailed. It's arithmetical and Macaulay, and there is one that I want to go on because this is very technical. The main thing is that if you consider the situation of the completely generic square matrix or the symmetric, then the dual is completely different from the Hankel case, including dimension. Now, I think, how much? How long do I have? 5? I think I want to skip a little bit this linear rank. It becomes a little bit technical. So it goes into syzygies, blah, blah, blah. It takes a while. We have some theorem here, though. Here's the theorem. It's a pity because there are so many things proved by Maral. I want to make some commercial. But anyway, whoever is interested can ask me for a copy of this. So this is the main thing. Generic Hankel determinant is not homaloidal, which means that the polar map is not a birational map. So one is based a little bit on this. One wants to show its Cremona. It's again, you know, this is how I was doing something about the linear rank, because it enters this proposition and then it's applied. Forget it. You know, but the problem is that it doesn't have the proper linear rank. You know, it doesn't have enough linear syzygies. Okay, this is the idea. So you cannot use this. Forget it. It's a nice criterion, cannot use. So you have to do something else. And the something else is to look at these Plucker relations. Although these are Hankel matrices, you can still look at the Plucker relation as if it were completely generic. And a bit, some of the things work. Like this, I call this factoid, homogeneous defining ideal of the case of algebra generated by the maximal minor. Remember that we can always translate now any question to maximal minors because this is an angle. So, so this is generated by Plucker relations. Where is the homogeneous defining ideal is generated by Plucker relations. And this is the only case. It's very stretched, you know. M minus 1, M plus 1. If you go out of this, totally false. We have other relations, sometimes even quadratic ones, but non-Plucker ones. And sometimes you may have some cubic ones. This is part of some other conjecture, which I will not show here. Okay, so here is a proposition that has been proved before with Maral, that if you are in the generic case, remember, if R equals 0, the generic case, then if you go that algebra that we looked about, that we looked at the degree of the respective field extension, this, at the level of the algebra, this is integral. So not just algebraic, integral. This is very strong. So the proof is to reduce to maximal minor, use Plucker relations, and then some more technicalities. So here's what we get at the end, that the algebra extension is in fact a neutral normalization. And this is now easy after you show that, because this is integral. And remember that this has maximal dimension and has the right number of generators, which equals the maximal dimension. So this is a polynomial ring up to some isomorphism. So this is a neutral normalization. Now, this is kind of fascinating for people that like reduction of ideal, is that the ideal of partial derivatives is a reduction of the ideal of the submaximal minors. And the polar map is not homaloidal. And Nivaldo Medeiros also announced the proof of this third assertion. His way of looking is totally geometric. I believe it's about the same, but I could not be able to translate to algebra. And the proof now is essentially easy because this is a polynomial ring. Homaloidal will imply that this would be inequality in this case. Okay, so maybe I finish with this comparison table. What is a comparison table? You compare Hankel with symmetric and generic. And you see that things go completely different. Maral, you came after I mentioned your theorem. Oh, you were here? So let this denote the, so I'm taking the matrix to be square. So this is the completely generic matrix. Huh? Variables throughout, different variables. And this is the same kind of matrix, except it's symmetric now. And this is the Hankel that we are studying. Now, I put this R here to compare just the degenerations. So I can degenerate this in the same way I did for the Hankel, and also the symmetric. So we have these three guys. And as before, this denotes the fiber cone for any of these cases, because I always have a determinant. So Fj is fiber cone of the gradient, and Fi fiber cone of the ideal submaximal minors. And now introduce this integer, which is defined this way. I don't have time to explain, but it will be the integer that you need to compute the number of specialization in the case of the symmetric matrix. So here's comparison. So here are the types. Here's dimension of the fiber cone, the polar fiber cone. I'm sorry, yeah. Yes, the dimension of polar fiber cone. This is the nature of the fiber cone. This is whether it's prime or not. And what is the nature of this inclusion? So you see for the dimension here for the generic case is m squared minus this. For the symmetric is this, with this integer. And here's maximum possible. So here's already a brutal difference because this is dominant over, this is the only case where it's dominant over the projective space, and this have a smaller image of this dimension -1 if you go geometric. And so this is the nature. Here it is one of these ladder Gorenstein complicated ideals. And this is Cohen-Macaulay ladder, but not Gorenstein. And this is just the polynomial ring because it was maximum. And here, what about prime? Here we saw that this is prime if and only if. Here, if this is true, if this holds, then it is prime. We expect that this is really the edge of it, so it's the only obstruction to be prime. Here we have no idea. This is a polynomial, this is polynomial, this is extension, and this is integral as you saw. So this is completely different. Okay, end. I hope they go along the conjectures, no?
Is there any chance for J to be equimultiple?
No. No, because J has this very small codimension. You see, the codimension is this rigid kind of thing that comes from the symmetric. You cannot do anything about it.
What if you replace Hankel by two Hankel? In the sense that two Hankel, three Hankel, n Hankel. The definition consider different configuration of the matrix. So it's like one by one.
Ah.
Go to a mode, you consider two steps.
You mean this kind of generalized catalectica? Yes. Okay. If you go to this, the paper that I mentioned with Maral, there are some results there. But again, completely inconclusive. So just expectations.
Finally, if there is some kind of hidden duality considering, because you have F, the determinant,
Yeah.
then you may consider the Jacobian ideal of the Hessian F. This gives you something in terms of
I don't know. Yeah. There's this classical result for a curve. Maybe something there, but I don't know. As I said, this the Hessian is something horrible, that the only way we can control it is by specializing the Hessian without specializing the original matrix, because otherwise everything degenerates too much. So we know how to specialize this in nice ways, and we expect to do it better for them. But this is just specializing in some ways, you know. We don't have any theorems about this. But it's a good question, this second.
I had a quick one. When you get the integral extension and the minimal reduction,
Yeah.
does it end up giving you any information about the reduction number or those degrees?
Yeah, I think we know the reduction number, but at this moment I forgot.
Look it up.
Maral, do you remember?
Okay. Fine. Thank you.
You see, this is the advantage of collaborating with young people. They recall.
You could put some invariant topological number, for example, projective dimension, and that.
You mean, it depends of what? Of J? Yeah, that's kind of difficult. It's very bad. You mean R mod J, or whatever the ideal, the ring. Yeah, don't know. I think Maral has something in the thesis, in one case, for the projected dimension. She worked on this in her thesis. But I think this was the case of R equals m minus 2, right? Yeah. Okay.
Any further questions?
Is this bound on R? You always have that the idea of the maximal minus is this one, right?
Yes, 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 yes. Problem is that in this case, in these two cases, you really have to work with the submaximal minors. And here, you can just work with maximal minors. That gives a nice handle in this case. But, you know, some of the theorems look similar the way you proved. Some of this follows from the notion of being one generic or two generic by David Eisenbach in that paper, you know, this, but not all, you know, some you can